6.2. This is called average value of a function. Average value of a function. Okay, so he says that seems really easy.
Is it?
Well, I don't know. Let's think about it. Average value.
Do we have every value of the function on
Oh, I should probably get my book out. That would be helpful. Possibly. Okay, so I want you to look at this function. Okay, I'm just drawing some willy-nilly function on here. Let it go from A to B. A to B. And I want you to think about having to find the average height of this function. Average height. So about how tall it is.
take every y value?
Take every y value and kind of start averaging them. Kind of sounds scary, doesn't it?
There's a lot of y values.
It's a lot of work. There's a lot of y values. Okay. Okay. Infinitely many y values. You ever had one of those sand art pictures? Anybody ever had one of those sand art pictures? Imagine that this is a beautiful sand art landscape of some sort, right? And imagine that I take it in my hands and I shake it down. What happens to this beautiful sand art?
There's empty space at the top.
Okay, there's empty space at the top, and what does it become? Flat. Noah's giving all kinds of hand motions back there. This is a flat sand thing that's not so pretty anymore, right? It's a rectangle. It's average height. Average height. Okay? And so what's the area of said rectangle? Area of said rectangle is base times height, yeah?
We have the base because we have the x.
Okay, we have the base because we have the x-axis. We have on an interval from A to B. You also have area of the function.
So we divide
What's area of the function?
The integral.
Oh.
So we divide the integral by the base and we have the average height.
Okay, so if I'm trying to find the height of this function, I could take area divided by the base, and I would be left with the height of this rectangle, yeah? Well, we already know the area under the curve. We know the area of the function. The area of the function is the integral on A to B of f of x dx. That finds me all of the area under the curve, right? Okay. The base of this rectangle, base, is going to be the length along the x-axis, b minus a, right? And so if I'm solving for the height, height is going to equal area divided by base. In other words, the height of this function is going to equal the integral from a to b of f of x dx divided by b minus a. Are you seeing that? Area divided by base. And the way that they write it in calculus is we can say the average height, f average. Average height of the function is equal to 1 over b minus a times the integral from a to b of f of x dx. This 1 over b minus a, this is the same thing as saying divide by the base. And this integral from a to b is the area. So again, if I wanted to find height, I take the area and divide by the base. There, sorry. Lauren was looking at the bottom. Do you see how the 1 over b minus a is the same thing as saying divided by b minus a? And there are a whole lot of notes here in this section on pages 490 and 491. Whole lot of notes, all to get to this one point that you got to in about 2 seconds. So I think we can go with this formula, average value formula here, and we can make it work for all of the examples that follow. Okay. One thing you need to know, and you're going to see this, in your AP test. They have average for two things. Average rate of change, you'll have to use your slope formula, y2 minus y1 over x2 minus x1. Average value of a function. So the word average gets used in two places, right? Average rate of change, that's old school secant line slope. Average value of a function, you're going to look for 1 over b minus a in front of the integral. That's how you know what we're doing. Okay? So categorize those two things, average, but they mean two separate things. Okay, so let's jump into example 1 here. Example 1, it says, find the average value of the function f of x, and I did not take any screenshots, so you're going to have to bear with me while I write it down. Example 1, find the average value of the function f of x equals 1 plus x squared on the interval from -1 to 2. On the interval from -1 to 2. And so really we just plug and chug. We go straight into our formula here. Average value of the function is found by doing 1 over b minus a times the integral from a to b of f of x dx. So the average value of this function is going to be 1 over 2 minus -1 times the integral from -1 to 2 of 1 plus x squared dx.
Why do we have to put b minus a on the outside?
We could divide by it, but that's going to be the same thing. This goes back to this slide right here, where you could have area divided by the base. The base would be b minus a. Or it's a little bit cleaner to pull that fraction, 1 over that, to the front right here. Okay, so it could be this way. That's a lot harder to comprehend than to just multiply it outside. So on the front, I have 1/3 times the antiderivative of 1, which is going to be x plus x cubed over 3. If you haven't done this step ever, you're wrong. Just speaking from experience, if you don't ever anti-differentiate, something's bad. And we're going to evaluate from -1 to 2. So I'm going to have 1/3 times 2 plus 2 cubed over 3 minus, open parentheses, -1 plus -1 cubed over 3. Two cubed is 8. 2 plus 8/3 plus 1. This comes out as -1/3, and I'm going to minus a negative, so plus 1/3. Am I doing this right? So I have 1/3 times 3 plus 9/3, which is also 3. 1/3 times 3 plus 3. 1/3 of 6. Final answer, 2. Yay, Brooks. He's back.
So that's it?
Mm-hmm.
So if you always say that.
So that's it.
And then he's like,
And then it always gets worse.
yes.
Look at the bottom of your page 491, the common error. Thinking that the average value is the secant line slope, when the average value is 1 over b minus a times the integral. Okay. If it wants average rate of change, there's your slope. Okay. You just got to know the difference, because we get all tangled up when we're taking this AP test and the word average pops out, and all of a sudden I don't know what to do. Okay. Neither one is hard. Look at the top of page 492. I super love the picture. They graphed this function that we just dealt with And they said, let's go from -1 to +2. And this function, it happens to look like this. And they found the average value of the function. And you can see it looks like that sand art. If you shimmy it down and shake it out into one rectangle, there you have your height. It would be at 2. Kind of cool. Do you understand what's happening here? Okay. All right, let's go on to example 2 then.
I wonder what the average height of this roller coaster is.
Ah,
I can tell you.
I could tell you. Yeah, take that roller coaster and shake it down. Example 2, it says average value involving a trigonometric function. So find the average value of f of x equals sine x on the interval from pi over 6, oh yay, halvesies, to 5 pi over 6. Halvesies,
It's more convenient than a normal number would be on a sine line.
right? Okay, so just envision, we're going from pi over 6 to 5 pi over 6. 6 pi over 6 would be from pi, right? So sine goes up through 0, and then by the time we get to pi, we're back down to 0. At pi over 2, it's up to 1, right? This is a sine curve. So we're really chopping it down, and we're saying I want the area under the curve from about right here to about right here. I want the average height. So I'm going to say when we shake that piece down, that's where it lands. Somewhere between 0 and 1, for sure.
Isn't that symmetrical?
Mm-hmm.
So like on that 2 points right there are those
I don't think we do know that it's symmetrical. I mean, you could go half of pi over 6. I think that's going to be overwork. I think that's going to make us work harder than we have to.
I'm formulating something.
Okay, you formulate. The rest of us will just do this example. So we have 1 over b minus a times the integral from a to b of f of x dx. So we're going to have 1 over 5 pi over 6 minus pi over 6 on the integral from 1 pi over 6 to 5 pi over 6 of sine x dx. Okay. And if you'll remember, we said the derivative of sine is cosine. The derivative of cosine is negative sine. We made this fun little chart that we could read backwards the other day. When we integrate up, the antiderivative of sine is negative cosine. Negative cosine. So they're going to have, what's 5 pi over 6 minus pi over 6? 1 over 4 pi over 6, also known as 4 pi over 6, could be simplified. 2 pi over 3. That is. Times negative cosine x evaluated from pi over 6 to 5 pi over 6. Not halvesies anymore. 1 over 2 pi over 3. Can we call that 3 over 2 pi? Are y'all good with that?
That's what Seth meant.
That's what Seth meant. So 3 over 2 pi times negative cosine of 5 pi over 6 minus negative cosine of pi over 6. Anybody unit circling here? Aren't these longs? And at 5 pi over 6, that's going to be a long left. So negative square root 3 over 2. But it's negative, negative. So positive square root 3 over 2. And at positive pi over 6, that's a positive square root 3 over 2. Now make it negative. Now subtract it. So plus square root 3 over 2.
Yeah. Okay.
I don't think we're wrong.
What? Hold on. What did he say for the second one?
This one, so cosine of pi over 6.
Yeah.
Cosine of pi over 6, that's going to be a short long.
Yeah.
I mean, a long short, and it's a positive short. But now I made it negative,
And then you
and then I distributed the negative.
Okay.
So now it's positive.
Okay.
Confused yet?
Yeah, I get it.
So we have 3 over 2 pi times 2 square root 3 over 2. 2 of those, ain't it? So I canceled those 2's. That made Bethany real happy. So I have 3 square root 3 over 2 pi as my final answer.
So I'll put that in calculator real quick.
Oh my god.
You want to verify?
Yeah.
You don't trust?
I do know.
Trust but verify. That's fair.
From my thing I was formulating earlier.
Oh.
Don't put that in the calculator.
0.826.
Dang it.
So it's not symmetrical.
So don't
Well,
it is formulate your
On
stuff.
height to height, it's 1/2 to 1/2 because sine of each one is 1/2. I was like, oh, it's going to be halfway between the half and the point where it's like a top one.
Mm.
But it's not.
But it's not.
I was going to give you 0.75.
Okay, also look at the picture in your textbook for this one. This is page 492. Look right underneath example 2. Can you see that that picture is this picture that I drew up here very smallly? Look, zoom in. Zoom in. Can you tell it's the same picture? Yeah. We understand what we found? Average height is like taking this function and squishing it down to be a rectangle. And then we measured the height. Okay. Y'all are not impressed. We're going to go on.
You are the next guy too.
Thank you. Michelangelo, that's what I want. All right, now example 3.
Yes.
Van Gogh's a little sad.
Also famous. And a Teenage Mutant
The
Ninja
Ninja Turtle?
Yeah, that's it.
Yeah, I don't know.
He's on Fortnite.
Wait, is he the orange one or no?
Yeah, he's the one who likes pizza.
They all like pizza.
He likes pizza.
No, they all like pizza. That's like your
Okay, so I want you to write down the mean value theorem for integrals. This is at the, we're talking about Ninja Turtles being named after famous Italians.
She said only one.
Donatello, Leonardo, Michelangelo.
I didn't know all that.
I thought the other people were named after them.
There's a bunch of Renaissance artists.
You didn't know that?
Honestly, didn't know I got the Michelangelo, but I didn't think about all of them. Leonardo.
Oh my god.
Mind blown. We have now connected the Ninja Turtles. Rico, I'm sure you already knew this.
Not as famous, but
Rico and Arlette.
So who's he's Raphael. Yeah, but
Well, they were Italian, so.
I'm confused.
Okay, that's, I know that.
Okay, we're writing this down. This is from the bottom of page 492. This says the mean value theorem for integrals. If f is a continuous function on a to b, okay, if f is continuous, then there exists a number c in the interval from a to b such that f of c is the average height. Okay, so we'll talk about it in just a second. Such that f of c is the average height. So f of c is equal to 1 over b minus a on the interval from a to b of f of x dx.
it's just me. If it's an average, then it's just me a line.
Okay, that is, there is some place f of c times b minus a that is equal to the area under the curve. Okay. It may not, but I'm going to help you in just a second.
That's good job.
Thank you. Thank you. Okay, so let this be f, y equals f of x. And let us look at this function on the interval from a to b. What this mean value theorem says is there's some point c somewhere in this interval where if I lopped off the top of the function, I could fill the hole and make the rectangle with the bottom of the function. Okay, so where's our average height? Where's our average height here?
Right in the middle there.
Right? Doesn't it feel like the average height of this function, if I shook it down, would be right in here? Okay. So there's some value C that if I cut off the excess from this piece at C, I could fill it in this hole.
Oh, okay, the midpoint.
So it's basically it's a midpoint idea. It's some point where f of C is equal to the average height of the function. But you can kind of eyeball it and tell where that's going to be.
So like A to C equals negative C to B.
Where I take the leftovers and I can fill this side of it.
I'm like that C is in between A and B.
C's got to be in between A and B.
Gross.
Okay, it's just not alphabetical. It's fine. Do you kind of understand what this is saying? So we're finding wherever that C value is such that it's equal to the average value of the function. So let's go on to example 3. Look in the middle of the page on page 493. Do y'all see the picture that I'm talking about right here? It says you can always chop off the top of a two-dimensional mountain at a certain height and use it to fill the valleys so that the mountaintop becomes completely flat. And that's the idea. There's some point where I can chop off all the tops and I could fill all the valleys and I would have a rectangle. We're finding that C value, where that actually occurs. So this is example 3. It says the function f of x equals 1 plus x squared is continuous on the interval. See, that has to be true. It has to be continuous on the interval. Otherwise, we're integrating something that doesn't work. So our function here is f of x equals 1 plus x squared. We are on the interval from -1 to 2. And the mean value theorem for integrals says there's a number c such that f of c is equal to 1 over b minus a. In this case, that's going to be 2 minus -1 times the integral from -1 to 2 of 1 plus x squared dx. There's some value c. And what do they want us to do? Find it. Find it. So I would say here that f of c is equal to 1/3 times the integral from -1 to 2 of 1 plus x squared dx. We've done this. We did already do this one, didn't we? So we found that this was 2. This was an example 1. F of c equals 2. So the question is, what is c such that f of c is 2? So what are we going to do?
Insert.
Set our equation equal to c?
Yeah.
Or set our equation equal to 2 and solve for c? We're saying f of c equals 2. Well, f of x is 1 plus x squared. So I'm going to say 1 plus c squared equals 2. Minus 1, minus 1. C squared is 1. So c is plus or minus the square root of 1. Plus or minus 1.
It looks like plus 1. Because it's to the right of the line.
So you have two different c values. Okay? I want you to look at the picture at the bottom of page 493. Right under this example, you see something that looks like this.
Oh, I was gonna do-
At -1 or at +1,
Oh wait, it has to be in between A and B, and A is -1.
okay, it has to be in between A and B. But I believe that since there are two values that work because it's in the interval between -1 and 2. So both of these c values work. But if we chopped off this function at x equals -1 at the height c equals At x equals 1, we're at height 2. Do you see that? F of c is 2. So when x is 1, I don't like how I wrote that. I wish I would have put F. Let this be C down here at the bottom, not F of C. Let this be C. At C equals 1, we hit that average height, which we knew to be true. So not only do we find what the average height is, which happened to be 2, but we find the x value that has that exact same output. That's the mean value theorem for the integral. Are we okay with this? Yes? No? Give me a thumbs up or a thumbs down. This is kind of iffy. Okay, I'll take it. We have one more example here. Here comes your physics. Same guy, right? Newton is kind of the dude for both. So example 4 says average velocity. Show that the average velocity of a car over time interval t1 to t2 is the same as the average of its velocities during the trip. So now you're doing two things. We're finding the average value of the function, and we're finding the average velocity, and we're saying they may be the same thing. So the average velocity of a car over time interval from t1 to t2. So average velocity, well, what's our velocity function? Okay, if I find the average velocity, I'm saying over t1 to t2, I'm doing 1 over t2 minus t1 times the integral, and I'm wanting to integrate the velocity function from t1 to t2. Can you understand that this formula would find me the average velocity? Average height of the velocity function? Right, this is exactly what we've just been doing. When I integrate velocity, what do I end up with? Position. Okay, so this is going to be 1 over t2 minus t1. And let's fundamental theorem of calculus here. If I integrate this velocity, I end up with s of t2 minus s of t1. Right? Those are the antiderivatives of velocity. Would be position. So this ends up being s of t2 minus s of t1 over t2 minus t1.
Hey, that looks like how we found slope. Average slope.
There's your average slope. Average rate of change.
Did they find this as like, oh, that's a cool coincidence, or like, this is how you come up with this?
And we don't know. It's just exactly like he says the derivative of momentum is the change in force. And we don't know if he meant F equals ma or if he meant dp dt is F.
He saw a graph and drew a secant line and was like, this is probably the average.
Average
Do you think
height
he
of
did
the
all
function?
that? Do you think he did all of calculus and then found out,
And then
"Oh,
realized
he's
it
found
later?"
something." We're going to teach this to 12-year-olds.
Pretty cool. Pretty cool. Any questions here?
Oh, that was it.
That was it. Yeah, our job here was to show that these are the same thing. And we did. It's kind of a non-example. But conceptual. Okay. All right, so that's all of 6.4. whatever number this is. 6.2. That's all. That's all of 6.2.